Part 3, finding the center of mass by integration. This is going to be very condensed, and your starting point in this particular problem was to start off by writing down an expression for the density of the rod as a function of position x. And what's different here is that you're going to start off with some constant term. So my density here now is going to be equal to alpha times x, so there's your proportionality constant, plus beta, where beta is going to be some kind of initial mass that you're adding on. Okay, and so this problem is very much like, you're starting with a rod, it's getting denser as you go, but you're already starting with some density at the beginning, and then it just keeps getting more and more and more as you go along. It's an analogy to this would be if you had a shape like a trapezoid, where you've got the top part, which is a triangle, that's going to be your alpha x, but then you're always adding the exact same piece down here, right, as you try to find those masses. And so that's your beta term here. The beta are those pieces. And then alpha x is going to be the part that's up here that's growing. Okay, so two different models of thinking about this. One of them is a rod that has an increasing density that starts from something that's not zero. The other one is to think of a trapezoid, and where is the center of mass. Now, hopefully the center of mass you're imagining is again going to be someplace over here. So my CM is going to be someplace to the right side of the middle. And again, it's probably more obvious if you look at the trapezoid, because you've got more mass at this end. So when we get our answer, we expect the answer to be something which is bigger than L over 2. I'm really going to kind of cheat on this one and just kind of show you the basic steps. Of course, you have to kind of write the differential version here. So lambda is equal to dm over dx. You rearrange it, and then you're going to take this and you're going to plug it in for the two integrals that you do. Okay? And so I really cheated here. I just drew squiggly calculus lines. And I'm going to say that you should be able to get these right, and you can check your work here by looking at my results. So take a second, and make sure that you're getting these particular results. Okay, you have two terms now because we added an extra term in the integral. So alphas are in there, betas are in there, L's are in there, and then you've got some fractions going on. When you divide these two expressions, you end up with your answer, which looks like this. It ain't pretty. You've got a lot of things happening there, and really none of them cancel out. So this is pretty much it. Just make sure that you can actually take these two expressions and kind of reduce them to this, right, when you divide them. So I did do a little bit of algebra to simplify things, but that's about as far as you can go. Okay, so that's it. Now, what you could do if you got that far and you're looking good, so you can now just verify this, and you can plug in some specific values. Make alpha 20 and beta 50 and the length 30. You don't really need the mass, but that's what it is. But if you just took those three values, you should be getting a center of mass position, which is at 19.3 centimeters. Okay, and compare 19.3 to 30. 19.3 is close to 2/3 of the way to 30. Not quite though, but it's close to 2/3. So I guess it kind of makes sense if you go back to our picture up here, right? If this is the exact 2/3 line, 2/3 L, the effect of adding this extra rectangle of mass is to actually bump the center of mass over a little bit this way. I'll exaggerate it, right? But if the length is 30, the 2/3 mark would be at 20. And our answer in this case is actually turning out to be 19, right? And that's because you've got the rectangle kind of evens things out a little bit and has a tendency to move the center of mass back towards the center, but not much. Okay? So our answer of 19 out of 30 is reasonable with the picture, and hopefully you can see why adding the rectangle caused it to move over closer to the center. Okay? So that is pretty much it. I think there's a couple more examples that you guys can work out for some more practice, but I'm hoping that this makes lots of sense, and it gives you three nice examples with the same procedure over and over. Good luck.